So consider the following circuit. Consider the following circuit. How many resistors do you have? A few or a lot? You have a bunch, okay? Now, question for you. Come on, everyone, focus. All right? Now, how many resistors do we have? No? How many resistors do we have? No. Count all of these zigzag lines. Okay? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10. Are they all connected? Are they all connected the same way? No. Let's look. Those two, just those two, are connected in what? Those two, there's a current split between them, so they're connected in what? In parallel. How about those two? What's up? I did? Okay, no problem. How about those two? Come on. How about those three? Okay. How about those? Do you remember I told you can embed one inside of another one? The general one here is what? But the inside of these two is what? Nice. Okay. Now, does anyone know what this is a symbol of? That's the what? That's the battery symbol. Now, every battery, everyone, every battery has a what? Has a what terminal and a what terminal? Has a positive and a negative. So the first thing for today, even though, by the way, did I tell you how strong the battery is? No, because the only thing in this question we're concerned with is to calculate the what? Only the equivalent resistance of this guy. Okay, but in general, a battery needs what? How many terminals? Two terminals. One is what? One is negative. Okay, today we need to learn which one of those terminals is positive, which one is negative. Would anyone like to take a guess? The long one is what? How many people say that the long one is positive? You're right. The long one on any schematic diagram for a circuit, the long one is positive. So go ahead and put plus here. Put plus here. Which means the other one is what? Negative. Go ahead. Okay, thank you. Now, yes, everyone. So there's something you need to understand about what? About electricity. The conventional, or the way they sketch what? Diagrams, say it, and we can say it this way, has been wrong since they've been sketching circuit diagrams. Now we know that which terminal gives electrons to the other terminal? Positive gives to negative, or negative gives to positive? Yeah, because negative means what? Negative means fewer electrons or more electrons? More electrons. And positive means what? Deficiency or what? Or lacking electrons. So they need to what? Flow from here all the way to what? To here. That's called the what? Everyone, that's called the physical current, because that's what really happens in what? In a physical, real system. However, there's another current called the what? There's called the what? The conventional. What does convention mean? When we have a convention, what does that mean? We had a meeting and we what? We convention, consensus. What does consensus mean? Exactly. All of us what? Have agreed on something. Conventional current has been what? Has been what the convention has been for hundreds of years. What is the conventional current? Weirdly enough, it's the what? It's the complete opposite of a what? Of what really happens. So it's interesting. When you design a circuit, you sketch it going from where to where? Sketch it. Going from where to where? Positive, yes. Or in this case at least, positive to what? To negative. But when you build the circuit, you know that the direction of what? Of the electron traveling is actually going to be the what? The opposite. It's been a mistake since the days. What's up? Of course. Okay, let's be honest here. What if you connect a circuit to another circuit? You need to know if one of them is going to what? Discharge or charge, which means you need to know how it circulates in physical, real, like reality. Make sense? It's been a mistake since the days of Benjamin Franklin, the American physicist, engineer, statesman who actually did so much with electricity. And ever since then, there's so many blueprints done with the what? With which current? Physical or conventional? Everyone, come on. What goes on a diagram? Physical or conventional? Conventional. What goes in real life? Great. So everyone, even though we don't know the what? We don't know the direction of we don't know the power of the battery here. Let's go ahead and sketch it. So just sketch it coming out of here. And I know it's circles, but let's say also what? It comes in here. Okay. The question here is simple. What is the what? What is the equivalent resistance of this whole circuit? If you would rather replace all of these resistors with just how many? One. how much of a single resistor exactly would you have to design? Okay, first of all, are all of them connected the same way or differently? All right, we have to divide them. So we have to chunk them up into what? Into groups. So everyone, let's go. Okay. Zeram, where would you say your first group is? And by the way, it doesn't matter where it is. Just pick a group. Yeah, like a certain number of resistors that form their own group. Where would you go? So you're saying that what? 10, 15, and 20 is a group. Now, is that the easiest group to choose at the beginning? I didn't think so. Which one probably would be an easy group to choose? 5 and 10. Okay, so everyone go ahead and circle 5 and 10. It doesn't, but my point is, I would rather not choose one with what? With mixed. That's all. So go ahead. Yes, you're right. 15 and 20 would be easier because of what? Because it's a single line. It's basically in series. But let's go ahead and circle this one. Everyone go ahead. Circle this one and say what? Number one. Number one. Okay, Baha, where's your number two? 15 and 20. So go ahead and circle this. Number two. Okay. Ali, where's your number three? 20, 15, and 5, the triple ladder. All right. And obviously, what leaves our last group? This one. 10, 15, and 20. The mixed. Okay. So let's calculate the what? The R equivalent of each single group. Of each single group. Okay. All right, everyone. So number one, number two, number one is here. Number one, number two, number two, I'm gonna put it right here. Number two, number three, number four. Okay, let's start. What is the kind of connection I have in number one? Come on, parallel or series? Is there a mix or is it perfectly parallel? Perfectly parallel. Sorry about that. Okay, let's do this. So everyone, all we're gonna do is on each one, I'm gonna give myself some grid lines. Yes, okay. So let's do the first one. So number one, what's the mathematical formula for in series? Sorry, in parallel. 1 over, thank you. So go ahead. 1 over REQ equals what? Do you flip and then add or add and then flip? Nope. Flip and then what? And then add the flips. So 1 over, what's my first one of that group? You're right. 5 plus 1 over. All right. 1 over 5 plus 1 over 10. Okay, keep going. What's 1 over 5 plus 1 over 10? Well, yep, that times 2, and this times 2. So we get 3 over 10. Now, is that my final answer? No, it's not. You can do one of two things. You can what? You can cross multiply. You can cross multiply, but I've never been a fan of cross multiplying for these calculations. I'd rather just do what? Flip the 1 over REQ, giving you what? REQ over 1, or just REQ, equals just what? 10 over 3. What's 10 over 3? And by the way, okay, you might ask me, what's the sig fig situation here? Well, I'm always going to give you what? How many sig figs? 3, or at least what? Even if it's a 10, I'm going to make it what? A 3 and so on. Everyone, everyone, listen up. Always make it to 3, please. Always make it to 3. Trust me, because you're going to add up to check at the end, and you don't want rounding to what? To keep building up. So go ahead, everyone, and make it to 3. What's 10 divided by 3 to 3 sig figs? 3.33 in what unit? In ohms. All right. Group number 2. Come on. Group number 2 is a pure in what? In series. So what do you just do? REQ equals how much plus how much? Sorry, how much? 15 plus 20 equaling how much? 35 ohms. I know you're saying this is only 2 sig figs. I know, but when we add up the whole thing, we're going to keep it to 3. All right. Group number 3. What's the deal with group number 3? It's a 3-line parallel, so I need 3 fractions. So go ahead. 1 over REQ equals 1 over plus 1 over plus 1 over. What do we have? 20, 15, 5. 20, 20, 15, 5. What's a common denominator of 20, 15, and 5? 60 is the lowest number they can get all the way up to. So go ahead, everyone. So 60 means what? I need a 3 here. Sorry, times 3 here, which times 3 here. I need times 4 here, and times 4 here. And I need times what? 12 here, and times 12 here. That gives me what? Over 60. That gives me what? Gives me 3 plus 4 plus 12. How much is that? 19. And what do? You flip like we did with this one. You flip to get 60. Hold on, let me squeeze. 60 over 19. What's 60 over 19? Well, I know one thing. It's 3 point something. Because 60 over 20 is 3. 60 over 19 is slightly more than that. 3.16. And let me just squeeze this one. So how much? 3 point? What's after the 6? So it's, oh, already? Okay, thank you. So 3.16 ohms. Oh, by the way, do you remember the logical check for your answer with an in parallel? For in series, it has to be what? Higher than the, for in series, higher than the highest. For this one, it has to be what? Lower than, smaller than the smallest. Well, apparently, I got what? 316. What's my smallest one? 5. Perfect. Checks out. Nice. And even for this one, 3.33 is less than 5. Nice. Okay. What's my last one? Ooh. What's happening here? What should be dealt with first? The level or the inside? The inside. Always what? Squish the inside first as if it were just what? Just one. So, yeah, go ahead. Yeah, but you don't have to show me a step for the inside because it's just a mere what? Addition of the two. Yeah. So as if this was what? Instead of 3, it was only what? 2. At 10 on top, but how much at the bottom? A combined what? A combined how much? 35. You got. Don't show me the 35 calculation step. You already. By the way, you want to feel free to show me a step that stands for n for that. Just show me this, and don't even call it a group. You see what I mean? Because it's a subgroup of a bigger group. That's all. Did you have a question or no? You're good. All right. So, but it's a parallel one. Bless you. So it's a parallel one. So number 4. What do I get? 1 over REQ equals how much? 1 over. What was the top? What was the top one? I'd just like to start from 10 plus 1 over. Nice. Hey, what's common between 35 and 10? 70. Thank you. This times 7. This times 7. This times only 2. This times 2. All right. So I got myself a 70 at the bottom. How much is that? 7 plus 2 is 9, which means R EQ equals 70 divided by 9. How much is 70 divided by 9? Well, 70 divided by 10 is 7. 70 by 9 is slightly more than 7. 7 point what? 7 point. 7 point. 70 divided by 9. 7.78. Is that, does that check out according to the imparallel logical check? Yes, it does. According to these two numbers, the lowest one is 10. 7.78. Done. What do I do with all of them now? Add them up. Nice. So R circuit equals, I think it was what? 3 point what? 3.33. 3.33 plus 35 plus 316 plus 778. How much is that all in ohms with 2 digits? Sorry, with 2 decimal digits. 49. How many people got 0.27? Just confirmation. Anyone? Come on, people. Well, you know what? Let's do it. 8 plus, sorry, 8 plus 6 is 4. 4 plus 3 is, yes. 27 approximates to what? 3. How can I check that this answer is correct? Ladies and gentlemen, let's have fun with what? With this one. Okay, so just pencils down once you're done all this. Let's build it on the what? On the website, on the FET website, PHET. Okay, all right, good. FET. Those are people with computer science and physics degrees. So they program basically simulations that run on a physics engine. Okay, let's do this. Come on. So okay, lots of them to go. All right. Okay. How much is this one? Come on. Okay, let's actually put. You know what? Let's do. It's gonna take a while to do, but it's okay. Mhm. I'm sorry. Yeah, yeah, exactly. Mhm. Okay. At the video? Yeah, yeah. Sorry. Oh, you're right. Thank you. Thank you. Mhm. This one's gonna be. Oh. You can. But I like to actually make it what as faithful to the diagram. Yeah, everyone, look. Um, Yasmin says, can you make this? Can you connect these two, like together, like the two? Yeah, you can because they are what like in series. But I like to always what give a space. Just my habit. Okay. Is that all of them? All right. Okay. What do I need to put here? No, a battery. Thank you. Do you see them moving? Yeah. Well, you know. Oh, what do you? By the way, what do you always have in any circuit you ever create? A real what? A real what? What's this? A light what? Switch. So even though we have a battery, if we want to control the flow, add a switch. There we go. Here's my switch right here. Is this an open or a closed switch? Open, close. Okay, let's change the values. Come on, everyone. What was this one? Top one, 5. Okay, how about the one below? Do you see what's happening to the bands? They're changing color. What was it, 10? Okay, how about this one? 15. This one, 20. How about this one? Sorry, 20. How about this one? 15. How about this one? How about this one? 10. This one, 20 or 15, doesn't matter as long as they are the same. How this one? How about that's it? Yes. Okay. Everyone, shh, come on. Okay, all of them are correct. What are we supposed to do here? Okay, so we are saying that all of these. Ibrahim, hold on. But we're saying that if I want to replace all of these, from here to here, with one, I should make it what? Okay, so let's create what? A smaller circuit inside of it, like right here. Here's my battery, same battery, of course. And I'm just gonna put a what? A wire and no more resistors. Oh, really? I never knew that. That's actually, I guess I never built up to 10. But okay, you know what? Fine, no problem. Let's okay. Now we have to what? Now we have to just insert a battery. Give me a voltage for the battery. 21? Sure, whatever one. You know what? Hold on, hold on. Wait. No, no, no. Wait. What's Ohm's law, everyone? What's Ohm's law? V equals what? V equals IR. Now, we built a circuit that has an entire resistance of how much? So we have V circuit, or V circuit must equal I total, like through the whole thing. So here and here and here, like in the single branches, I total times R of what? What was the R of circuit? 49.3. I don't know this one. And also I don't what? But at least I can insert what? I can insert a battery. Let's say that the battery is 120 volts, okay? Which is the maximum battery apparently number that you can actually choose. So I'm gonna choose this as what? What? 120, okay. How would I know how much current is traveling in this circuit? Yes, so I equals 120 divided by what? 49.3. Go ahead, tell me how much is that? 2.43. In what unit? It's a current, so it's in amps. Okay, you know what? Let's insert it. So let's completely forget about this one. Delete. Okay, so go ahead. We said 120, right? 120 all the way up. Okay, now what do I do to the switch now? Close it and allow them to move. They do move, right? Okay. I need to measure the what? I need to measure which one of these two devices measure current, a voltmeter or an ammeter? Ammeter, okay. How do you measure current? Okay, how do you measure voltage? You just walk with how many hooks? With 2 hooks, and you touch how many times? Twice. And wherever you touch, it's going to tell you the voltage what? Difference. The voltage difference. Ammeters, you don't have what? You don't have hooks. You need to what? You need to cut it and what? And put it in. Now, could I put it here? No, that's not good. Not good. Not good. You put it where? At a single wire. So where could I cut? Yasmin? Tell me where could I cut? Only Yasmin. I cannot cut inside of a loop. I need to cut at a single wire. Sorry, say again, where? You mean here? Oh, okay. Okay. I need to measure only the wire itself, by the way. Okay, how about I cut here? Is that good? Okay, everyone, let's cut there. So I'm gonna cut here. Okay, you know what? How about we cut here? All right, yeah, let's go. Again, I have to get what value? I have to get 2.43. Well, let's see if I still have a job. There we go. How much? 2.44. 2.43. But is it, you know why? Because this one is what? Rounded up. This should have been what? Remember? 2.7. If you make this smaller, what happens to the whole thing? It goes higher, and it's going to make it to what? To 2 points. But is it making sense? How do I check now? I remove all of them and add one single resistor for how much? 49.3. I better replicate exactly how much current. Do you see what I mean here? And equivalent resistors mean what? If you take all of them and you insert that, the battery sees what? No change. Is it making sense? The battery has no idea that you did anything. Okay? What's up? I'm sorry? Oh, okay, everyone, listen up. Yasmin is asking, why did I not use the voltmeter? Because it's not the volts I'm trying to measure. I'm trying to measure the what? Yes, see, I designed the voltage. I need to measure the what? If I did the other way, then you're right. If I already decided on a current, I what? But by the way, do you ever decide the current or do you measure the current? What do you always decide? You always decide the battery. The current is the what? The current is what comes after you combine this one and this one. Is it making sense now? All right. What do I do with all of these resistors? Come on. Delete them. Well, I just need to delete a couple because I just need one resistor to appear here. Or hold on a second. Can't I just duplicate the... Oh, damn it. I reloaded it. Okay, whatever. All right. Battery, wire, resistor, and I guess I can just go like this. Ta-da. All right. Now my battery has to be how much? And my resistor has to be how much? 49.3. Okay. How do I check? I need to measure the what? I need to measure the amperage. I need to measure how much current. And it better come out to what? 2.43. Me indicating that what? The circuit has not seen any change. All right, what do? I cut and I insert this guy. Ready? Look, everyone, eyes on the screen. System works. Is it making sense now? What's up? It's again, more or less, it's the same. All right? Okay. Now we do what? Now we actually what? Calculate voltages and currents, not just resistors. Now we analyze a circuit from head to toe. All right. السؤال what's up جوه resistor yeah go oh it's gotta be less it has to be yes exactly and because they already split too that's exactly what I gotta do right now okay everyone come on let's do this one now okay come on Shh. Let's put all of everything we learned in this unit to one final example, calculating everything we need to know about a full circuit. Okay, what does the question say? Consider the following circuit. Assume all values are to what? 3 sig figs, input and output. Okay, let's look. So I have what? A bunch of resistors. Great. Do I know my battery though? Yes, I do. Okay, let's put the plus minus. Everyone, which one is plus? Which one is minus? Come on. Hold on. Long side is? Go ahead. Long side is plus. Short side is? Okay. Conventional. How does it go from where to where? From the wrong one to the correct one. And by the way, everyone, listen up, just so you know. Some people say, oh, so it just goes this way. Why do you think they might think it goes this way? Because they think it's plus to minus, but it never goes through the battery. It goes through the what? It goes through the circuitry itself. Thank you. Very good. Okay. So go ahead and okay, let's sketch all of them. Come on. Goes in. Then what happens? Splits and comes down. Goes through. Goes through. Come on, come on. Add all of these up. Goes through. Splits. Goes out. Comes in. I like to call this method the tracing method. Because legit, we're doing tracing of the whole thing. On a diagram, we always go by conventional. I don't care whatever physics you do, you always go conventional. Then, sorry? Yes. Okay. Okay. Step one. What the, everyone? Yasmin, what does part A say? Part A. What does it say? On the circuit. Done. Full marks. Everyone. Part A, we got done. Sketch what? Sketch arrows to tell me how the current is what? Circling around in the within the circuit. Within the circuit. Got it. Is this clockwise CW or counterclockwise CCW? Is it with the clock or against the clock? It's against the clock. Perfect. So go ahead and just circle CCW. Against the clock means counterclockwise. Counter means against or opposite. So go ahead and just, it is going counterclockwise. Okay? Question B, calculate the what? You have to assume that you what? That you compressed the entire circuit to one single resistor. Okay? Let's put the groups. How many groups do I have in this circuit? All right, let's see. I guess I have my big group here, right? Sorry, let me zoom out. I have my big group up here. This is my group. This is group one. This is one group. This is another group. This is another group. Come on, where's technically my fourth group? This single one. I can count it as a group. Who cares? Or I can what? Not even pay attention to it until the very what? Until the very end when I add all of them up. All right, let's do that. Let's not call it a group, okay? Because what's a group of one? No addition, nothing. It's itself. So go ahead. Let's I guess let's call this group number one. Everyone, this is group number one. So just put number one. Let's say this is number two. And this is number three. Okay, tell me the calculation for group number one. Come on. Tell me the calculation for group number one. Is it series or parallel? All right, it's 1 over 1, 1, 1. Okay. All right. Group number one. 1 over REQ equals what? 1 over plus 1 over plus 1 over. What are the three numbers that we have? We have 50, 20, 40. 50, 20, 40. Hey, what's common denominator, my bad. Common denominator between 50 and 20 and 40. If it was 5, 2, and 4, it would be 20. So if I add a 0, I just add another 0. Nice. So everyone, we're going to get a 200. So 1 over REQ equals something over 200. Now, what would need to be done? This is times 4, and this is times 4. This is times 10, and this is times 10, and this is times 5, and this is times 5. What do I get? 4 plus 10 plus 5. That's a 19. That's a 19. So what's my answer here? REQ is equal to 200 divided by 19. How much is that? 10 point something. Sorry, 20 point something. Oh, my bad. We're dividing by 20. We should get 10. 10 point what? 5.2. Thank you. 5.3. All right, everyone, 5.3. Oh, when we do our final answers. When I do my final answers, all my final answers for the REQ of the whole thing, V of the whole thing, and so on is 3. Yes. Yes. Okay, group number 2. Come on. Group number 2. What do we have in group number 2? And how many values? 2 values. Go, go, come on. Come on, you didn't need me for this. 1 over 30 plus 1 over 60. Come on, what's common? What's common between these two? 60. So I just need to change this guy. So 1 over REQ equals 60, and you get what? 3. Nice. So REQ is equal to what? 60 divided by 3, which is how much? How much? 20. I'm just going to keep it as 20, even with one sig fig. I'm just going to worry about the sig figs towards the end. All right. Next one. What's my group number 3? The big one. But the big one is what? Look, the big one, is it pure or mixed? It's mixed. What do I have to squish first? I squish the ones on the same line, adding to 70. Thank you. Awesome. So 1 over, what's the top one though? 20. 1 over 20 plus 1 over 70. What's common between 20 and 70? Come on, 7 and 2. What's common between 7 and 2? 14. So 140. You're right. So, oops. So this multiplies 7. This multiplies 2. What do we get? What do we get? What do we get? 140. And how much do you get? 7 plus 2, which is 9. So REQ is equal to 140 over 9. How much is that? Well, 1 over 140 over that divided by 10 is 14. We should get 14 point something. It makes it to 15. Okay, great. 15.55. So I'm assuming it's 5.6. It's 5.555. Yep, 5.6. So much. What's my overall? What do I do? Add them, and don't forget about the what? No. Don't forget about what? The single standalone one. Yes. So R circuit. Everyone call it R circuit. R circuit equals 1053 plus 20 plus 1556. And what's the standalone one? 30. How much is that? To 3 sig figs. That is to 3 sig figs. What are we talking about? 78 something maybe? Yeah, I think so. 20 and 30 is what? 50. 50 and 10 and 15 is 75. 76 point, yes, 76.09, so 76.1. Thank you. Okay. Once you get to that, please put the pencils down. Am I at this stage now? Do I know the resistance of the whole circuit? I just did. Do I know the voltage of the original battery? How much? Can I calculate the what? Can I calculate the current running in the single wires everywhere? How? V equals IR. Look at what question C says. On the circuit, determine the what? Oh, sorry. No, hold on. Oh, okay. Okay, question for you, everyone. Listen up. Question, pencils down. Other teachers, listen up. Other teachers, when they give you a question like this, instead of giving you what? Look. By the way, did I give you a lot of space or nothing? Other teachers give you what? A table of what? All the resistors, and they number them. By the way, how many resistors do I have? Just count all the resistors. Come on. How many actual single resistors do I have? I have 9. They give you a table of how many rows? 9 rows. R1, I1, V1. Do you see what I mean? And they tell you, tell me the for the R1, tell me the current through it and the voltage what? Across, and so on. I don't like that. I want you to put it all on the what? On the what? On the diagram. On the diagram, okay? But there's only one thing we can write here. It's which calculation? It's the I total calculation. Go ahead. That's the only thing you can put here. All right, let's do it. So I, go ahead, I total equals, what's the battery power? How much? 120 divided by, what's the full thing? 76.1. How much is that? 1 point something. It's got to be 1 point something. 120 divided by 76.1. 1 point. I need to only keep 3 digits. So how much? 1.58. Nice. So that means if I build this on the app, on the website, I should get 1.58 in the ammeter reading. No, that's it for what? For knowing, everyone, look, that's it for knowing how much amperage is what? Coming out of the battery. Okay, everyone, listen up. Pencils down. Watch how am I going to do the first group. This is what I like to call the tracing method. Okay, please don't copy anything. It's already recorded. Okay, you mind just focus on me here. Okay, everyone, let's look at the diagram. Come on. How much is coming out of the battery? We just calculated that. No, no. What? No, no. Hold on. Okay, wait. Everyone, listen to the way I'm saying it. The battery voltage is 120. But whenever I say how much is coming out, I'm always talking about current. Whenever I say how much is coming out or going in, current is the only thing that moves around. Voltage is fixed. Current is the what is the flow. How much is coming out of the battery? 1.58 A's. Okay, so everyone, don't copy. Don't copy. Let me see how much space you need for the copying. Okay, so right here, everyone. Now I'm gonna take this out. And how much am I gonna put here? 1.58 amps. Okay. Question for you. Is this 1.58 in here, in here, in here, or in all three? If someone says, oh, 1.58 here, that's also 1.58 here, 1.58 here, does that make sense? It splits. Now, what do we know about the split? It splits in such a way, if I add all of them, I get how much back? Okay, you see how it's the wire hose principle? If you have a wire hose and it goes into how many branches? 3. Not all of them get all of this. This gets some, this gets some, this gets some. But when you add all 3, you should get what? What if you get less? What does that mean? There's a what? There's a leak. What if you get more? That makes no sense. Do you see how conservation of mass is kind of like conservation of what? Do you see what I mean here? Logic is the basis of physical thinking. Okay, here's my question though. How am I going to know how much splits up, splits middle, splits down? I have a question for you. How much is coming in? Right here, everyone. Right here. What's the current? Right here. And does this 1.58 go into one of them or the whole group? Okay, hold on. So, but my point is, do I know how much is coming into the whole group? How much? 1.58. Do I know how much is the resistance of the whole group? Interesting. V equals what? Do you see how we're going to keep doing V equals IR through the whole thing? Yes. So everyone, look. Do I know the resistance of group 1? Do I know how much current is feeding into group 1? So what can I calculate? The voltage of group 1. So let's actually do that where? Right here. Right here. Maybe here. V equals what? Come on. V equals. What's my I? 1 point what? You're right. Of that group. Exactly. Oh. No. I need to know the voltage of the whole group first, and then I'm going to calculate the voltage and the current across each one. But I need to know the voltage of the group first. What's 1.58 times 10 to the 53? It should be 11 point something. Or hold on, no, what am I talking about? 16 point something. Okay, so let's go with what? 3 digits. 16 point. No, just 16.6. That's what I mean. 3 full digits. 16.6. In what unit? In? Oh, no. Way too much accountability for the sig figs here. Okay, everyone, listen up. Do you want to hear some good news? No, seriously, some really good news. For circuits, at least. When you have listen up. Don't listen to him. When you have a parallel or a stack, guess what? Whatever you calculated here, I'm not kidding. This is probably the best news in all of circuit. Whenever you have a stack, the number you got here is also the number here, and the number here, and the number here. For the price of 1, you get how many? Okay, what if you had a stack of 4? For the price of 1, you get how many? What if you had a stack of 100? For the price of 1, you get how many? No, if you had 100. Do you see what I mean? Isn't that good news? In one shot, you already know the what? The voltage here, the voltage here, and the voltage here. No, in series is different. In series, it's the current that's the same because it doesn't split. In parallel, it's the what that's the same? The voltage. Always remember that. The good news is when you have a ladder, all the steps of the ladder have the same what? Have the same voltage. All right, let's put it in each one. Where do you put it? I don't really care. Let's actually just put it on the side. So 16, go ahead. 16.6 V. Go, come on. 16.6 V. 16.6 V. Okay? Now that's interesting. I know how many things about this one now? I know two things about each resistor. I know its resistance, and I know it's what? And I know it's what? Its voltage. What can you calculate always when you know the resistance and the voltage? I can calculate the what? The little amount of current that what branched off, branched off, branched off. Okay, let's just do it. You know what? Let's not even sort the calculation. We know what to do. Let's divide. So are you gonna divide this by that or this by that? Come on. You always divide the V. The V is the big one. The big one as in not number, but the big one as in product. So you divide this by either one of these two. So what's 16.6 divided by 40? Go for it and give me what? Give me again 3 decimals. 3 decimals because you're going to get something less than 1. 0.415. Baha, in what unit? Ohms, volts, amperes, amps. Okay, how about 20? I know it's half of that because if you divide 40 by this and you divide 20 by that, you should get half, which makes sense. Yes. 0. What? 830 amps. How about that one? 50 divided by that. 50 divided by that. Come on. Point what? Oh, sorry. I mean 16. Sorry. 16.6 divided by 50. My bad. 0.332. Okay. Hold on. Everyone, stop. Before I leave this group and go to the next group, how should I check that my answers make sense? If I add all of them, I should get super close to what? Okay, let's add them up. 100%. Again, that's why you know if you are within a single decimal, you're fine. So go ahead, let's do this. So 0.332 plus what? 0.830 plus what? 0.415. Come on, it's 1.58, right? Okay. Oh, everyone, question for you. Ali, look. Was there another way? Check this out. Was there another way to find this without dividing? What equation? Then, come on, man, put it to words. So, Zegham is trying to say it, but he's too mathematical to what? To simplify it. What you're trying to say is what? How much is this? It splits into how many branches? I already know this one and this one. What's the only way to know this one? Add and what? Subtract. That's what you want to say, right? Because you said that was a variable, right? Okay, everyone. Can someone add these two for me? Just add these two. Just add 0.830 and 0.415. Come on. 0.88, like add the middle branch and the bottom branch. Just those two. Great. Go ahead. Minus 1.58. Minus 1.58. How much do you get? Forget the negative. Forget the negative. Nice. Do you see what I mean here? It's this, again, logic. If I have a hose that splits into how many? 3. This one stole some. This one stole some. How much is left for this one to steal? You add these two and you what? Subtract from the total. Now, which one is more accurate, do you think? Subtracting these two from the total or dividing like we did? How many people go for dividing? No, no, no. Well, I trust logic, and logic is conservation of mass. I trust it as well. Here's my, I'm asking, which one would be the more accurate approach to get these two done and then subtract to get this one, or to do the same thing, divide, divide, divide? I think we should divide. You know why? What if you made a mistake in one of these? Then if you subtracted, you would also get what? A mistake in this one. But if you divide, that means what? The mistake would not carry. You see what I mean? That's all. All right. Are we gonna do this the same way? Come on. Okay, Yasmin. How much is going in right here? Right here. How much current is gonna be measured right before it touches? Sorry, right before it splits, I mean. 1.58. Come on, everyone. That's why I call it the tracing method. If my prof in first year physics did it this way, I would not have kept failing circuits for the entire physics course. It didn't make sense because he was just putting the numbers in. And he would never say splits and comes back. I'm like, why don't you? You're teaching physics. You're teaching nature. Show me a picture. Nope. It was all in his mind. Kind of like you when you said variable. Okay. That's why you always need to what? Simplify. So how much is here, Yasmin? 1.58. Okay. How much is the strength of the whole group? 31 point. Yes. So where should I put the calculation for it? Let's put it down here maybe. Sure, yeah. V equals 1.58 times, what was it? Sorry? 31. Oh, no, no, no. What was the resistance? I will show the calculation. 20 exact? Nice. Okay. How much is that? 31.6 volts. What's the good news again about any stack? Once you get it once, you get it for all members of the stack. So I'm going to put it here, everyone. 31.6 V, 31.6 V. And then what do I do to find how much current has split? Divide the V by the ohm. How much is 31.6 divided by 30? 1 point something. How much? 1.05 amps. Come on. This one is twice as resistive. What does that mean? When you're twice as resistive, do you allow half as much or twice as much? No, no, no. When you're twice as resistive, you allow only half the electrons. I guarantee you're going to get half of that, which is point what? 0.53. Come on. If you add this one to this one, what do you get? 1.58. The system never fails. This is how the universe works. Okay. Ooh, what about this one? Okay, I know it looks more complicated, but is it really? Everyone, come on. Do I really need to look at this right now as 60 and 10? Or could I just look at it as a 70? Okay, but I'm not even looking at it anyway. Am I on the inside or still on the outside? You always are on the outside. And as far as you're concerned at the outside, you don't even know what's on the inside. So again, what would this one be again? 1.58 amps. Okay, V equals what? 1.58 times, what was the strength of this group? 15.56. How much is that in V's? That would be 25, 26 point something. Sure. 24.58. I'll go with 24.6. 24.6. Now, what's okay, everyone? What's the good news? Again, what was the good news always? But my problem is here. I do not have one. I have what? So let's not look at this now. Do I know for sure that the voltage here is that? Okay, let's do that first. Forget it, everyone. Yes, you already know the answer. I'm just showing it to you how to actually what arrive at that conclusion. I am going to completely look at this one first, see how much current it steals, and then see how much seeps down here. You are right. Yes. And that's, okay, do you see how many ways there are to do it? Yes. Yes. Okay, so let's do the top one. What's the top one? 24.6, of course. I need someone to divide 24.6 divided by 20. 1 point something. Okay. 1.23 went up here. How much is left to go down here? we're going to divide, sorry, not divide. We're going to subtract 1.58 minus what? 1.23. How much is 1.58 minus 1.23? Now, is there a split here? No, here. Which means what? Whatever goes in here is the same as whatever goes in the middle as whatever goes in here. What does that mean? No need to write it both times. Just write it in the middle. Just write in the middle. Basically, you're saying that it's the same for both. So go ahead. Point what? You said point? 0.35 amps. Okay. Instead of me knowing voltage and resistance and having to get amperage, what do I know about each one now? Amperage and I get what? I get the voltage. Come on, let's get the voltage of each one. How do you do the voltage? Are you going to divide these two or multiply? What do you do with these two to get V? I know. I'm going a bit too fast. Look, Yasmin. I know the resistance of this guy, right? And I just found out how much current is going through it. Exactly. Multiply. Yeah. How much is 0.35 times 10? Come on. 0.35 times 10. 3.5. Everyone. 3.5 volts. Come on. 3.5 volts across the first one. How about the next one? 0.35 times 60. How much is that? 6 times as much, which is how much? What do you get when you add 21 to 3.5? 21 to 3.5. You're right. You're right. It's the same. I am Bob back here. Work. I did say. What's my last one? Come on. What's my last one? This standalone. Come on. Does this one have any splits? Come on, everyone, listen up. Does this one have any splits? No. How much is fully going through? How much is fully going out? 1.58. So this is only a single calculation. Go ahead. 1.58 here. And we just need to multiply 1.58 times 30. How much is that? 40 something? Oh, from here, Yasmin, we had to get the what? We had to get the full resistance of the whole circuit, and then we, after adding all the resistors, yes. And then we divided the what? Look, the voltage of the whole battery divided by the resistance of the whole battery. It is. No, Yasmin, you talk about the first handout. In the second handout, it is here, 120 volts. Yes. Yes. Okay, can someone tell me what this is? Come on. 47.4 volts. Oh, to check. Yeah, I got it. Okay, everyone. Last step that you always need to check. Listen up, pencils down. Everyone, pencils down. This will take 1 minute. What is the voltage strength of the whole battery? I need to check that all of these voltages add up to what? But hold on. Many of you, no, it's not, you see, okay. Baha is concerned because like, am I going to add all of these V values? No. You're only going to add them for what? For each group. You're not going to add this 3 times. You're only going to add it once. Where? So how many voltages are we going to add? 4, because we have how many groups? 4 groups. We're going to add what? 16.6 plus what? 31.6 plus what? Plus what? As long as you get within plus minus 1 of this guy, that means you're good. Let's do it. Come on. Okay. So, what do we get? Let's see. How much is, it doesn't matter. You know, 16.6. Come on, help me out. 16.6 plus 31.6. Come on. Plus 24.6 plus 47.4. What is the whole thing? How much? 120.2. Perfect. We're only off by what? 0.2. Perfect. Within, as long as you get no more than 121 or less than what? 119, you're good. we're done circuits.